Think about it for a second. Take any law of physics, any equation, and reverse time. Make the clock run backward. What happens? Newton? The laws of motion work perfectly in reverse. Two balls colliding, filmed in reverse, look completely normal. Electromagnetism? Maxwell's equations are time-symmetric. They don't care which direction time is flowing. Quantum mechanics? Schrödinger's equation evolves equally forward and backward. General relativity? Einstein didn't care. Space-time has no preference for which way time flows. Now imagine two teacups clinking against each other. Filmed in reverse, it looks normal. Nothing special. Now, take a raw egg. Crack it into a frying pan. Film it. Play it backward. The broken egg reassembles perfectly. The yolk slides back inside. The intact egg jumps into your hand. Absurd. Impossible. Ridiculous. But why? The molecules of the egg obey the exact same Newtonian laws as anything else. There is no law of physics forbidding the egg from reconfiguring itself. In purely mechanical terms, all the atoms could, technically, move back to their original positions. Except, it never happens. Ever. And that is the huge problem. If every fundamental law of physics is time reversible, if reality doesn't care which direction time flows, where does this asymmetry come from? Why doesn't the cracked egg go back? Why doesn't the smoke go back down the chimney? Why does the universe seem to have a clear direction, a distinct past and future, if none of the fundamental laws recognize this difference? The answer is a single law. Just one. In all of physics, there is exactly one law that is not time reversible. That distinguishes past from future. That creates what we call the arrow of time. And the most terrifying part? That very same law has already written the end of the universe. Not as a possibility. As a mathematical certainty encoded since the very first instant of the Big Bang. The end of time isn't coming. It is already here. Let's understand why. First of all, I need to destroy an idea you've probably been carrying around for years. When you think of entropy, you think of disorder. Things get messy. Rooms get cluttered. That's the popular explanation. It's technically wrong in the way that matters. Rudolf Clausius, a German physicist in the 1850s, was the first to formalize entropy. He noticed something simple but powerful. Heat always flows from hot to cold. Never the reverse. You don't drop an ice cube in warm water and watch it get colder. You don't walk into a cold room and feel your body heat flowing from the walls into you. Heat moves from hot to cold. Always. That's not a preference. That's one of nature's iron laws. Clausius saw something profound here. A direction built into reality that no fundamental law could explain. In 1865, he formalized it. The entropy of the universe tends to a maximum. But it was Ludwig Boltzmann who actually figured out the why. Forget disorder. Here's what matters. Any macroscopic state can be made by countless different microscopic states. A whole egg? One specific molecular arrangement. A cracked egg? Trillions of different ways to arrange those same molecules and get something broken. Any random combination of molecular positions produces a shattered egg. Boltzmann formalized this with an equation that was engraved on his tombstone. S equals K times. The logarithm of W entropy is Boltzmann's constant. About 1.38 times 10 to the power of negative 23 joules per Kelvin, multiplied by the logarithm of the number of available microstates. That W is the number of distinct microscopic ways to arrange a system's particles to produce the same observable macroscopic state. Watch this W in action right now. Drop ink into water. It spreads. It never concentrates back into a spot. not because physics forbids it, because the spread states outnumber the concentrated ones by a factor so huge it stops making sense. This is Boltzmann's W, not just an equation. You're watching it happen. And suddenly, the second law isn't mysterious. It's just math. If you have billions of particles moving randomly, they won't spontaneously organize into a specific, improbable state. They'll explore all possible states with equal odds, and there are vastly more high-entropy states than low-entropy ones. The ratio is literally astronomical. Here's the scale. Shuffle a standard deck randomly. The odds of getting factory order? 1 in 8 followed by 67 zeros. Now imagine that calculation for trillions of molecules in an egg. The egg doesn't unbreak not because physics forbids it. It's because the probability is so insanely small, it stops making sense. Here's the truth. The second law of thermodynamics isn't exactly a law. It's an overwhelming statistical reality. The universe moves toward more probable states. Technically, it could do the opposite. In practice, never. Here's what keeps physicists awake. If entropy is just probability, if the universe always moves toward more probable states, why did it start in such an incredibly improbable one? Why did the Big Bang begin in such a low entropy state that 13,800,000,000 years later, we're still nowhere near equilibrium? That question has an answer. But the answer is even more baffling than the question. And to understand where it comes from, you need to know the man who spent decades wrestling with exactly this issue and was destroyed by it. Ludwig Boltzmann spent his whole life defending an idea that seemed obvious to him and absurd to everyone else. Atoms exist. Today, that seems elementary. Of course, atoms exist. But at the end of the 19th century, there was a serious philosophical battle over whether atoms were real or just convenient mathematical fictions. Ernst Mach, one of the most influential thinkers of the time, argued that only the observable mattered, and atoms were unobservable back then. Boltzmann didn't just believe in atoms, he built the entire field of statistical mechanics on top of them. In 1872, he published the H-theorem, a mathematical proof that entropy must increase over time, derived directly from the individual interactions of particles. And then came Joseph Loschmidt with what became known as the reversibility paradox. The argument was devastating. If every particle collision is perfectly reversible in time, and it is by Newtonian mechanics, how can you have a theory that's irreversible at the collective level? If you reversed every particle's velocity at the same instant, mechanics says everything would evolve backward. Entropy would decrease. The egg would unbreak. And this comes directly from Boltzmann's own laws. Boltzmann was thrown into crisis. His way out was profound. The H-theorem works, but it needs a special initial condition. Low entropy. Start with low entropy. Particles disperse into higher entropy. But that just pushes the question back. Where did this initial low entropy state come from? For decades, Boltzmann tried to answer that. He proposed that the entire universe could be a random statistical fluctuation in an infinite cosmos in equilibrium. Our pocket of low entropy would simply be a rare but inevitable accident over sufficiently long timescales. The scientific community rejected it, attacked it, ridiculed it. Conferences became confrontations. Correspondence grew hostile. In September 1906, during a family vacation in Duino, Italy, while his wife and daughter were swimming, Ludwig Boltzmann hanged himself. He was 62 years old. 3 years later, in 1909, Jean Perrin published definitive measurements of Brownian motion, the erratic movement of microscopic particles suspended in fluids. Perrin proved mathematically, with experimental precision, that atoms exist and had exactly the properties that Boltzmann predicted. Boltzmann was completely right. Every detail of statistical mechanics confirmed. The theory he defended his entire life, which consumed him psychologically, was the correct description of reality. He never knew. But the battle Boltzmann fought revealed something fundamental. The second law was much stranger than anyone had imagined, and others were already trying to tear it down through completely different means. 18 years before Boltzmann died, James Clerk Maxwell proposed a thought experiment that almost destroyed the second law. Imagine a box divided by a wall with a tiny hole, both sides filled with gas at the same temperature. A tiny demon guards the hole. The demon watches molecules approach. When a fast, hot molecule comes from the left, he opens the hole. Fast molecules go right. Slow molecules go left. Over time, the right side heats up. The left side cools down. A temperature gradient appears from nowhere, with zero work. This violates the second law. Entropy decreased. The demon used pure information to reverse the natural flow. For 80 years, nobody solved it. Think about that. Here was an argument that, if true, destroyed one of physics' most solid laws. And for 8 decades, not a single physicist could refute it. Maxwell posed it in 1867. Quantum mechanics happened. Relativity happened. The nuclear age happened. The demon still stood. The solution came in 1961 from Rolf Landauer at IBM. His insight was clean. The demon needs memory. It records information about each molecule, speed, position, decision, to know when to open the hole. This memory has finite capacity. Eventually, it erases old information to keep going. And erasing information costs energy. Erasing 1 bit releases at least kT times the natural logarithm of 2 of heat. That's Landauer's principle. A fundamental physical limit, not a tech problem. Add up all the heat the demon generates erasing memory, and the total entropy, demon included, increases. The second law survives. But Landauer revealed something bigger. He showed entropy and information are the same thing. The exact same physical quantity, different units. The more you know about a system, the more specified it is, the lower its entropy. Information and entropy are opposites. Entropy isn't just heat. It isn't just disorder. It's a lack of information about the microscopic state of a system. This is going to matter more than you can imagine in a few minutes. Here's a simple question that isn't simple. Why do you remember the past and not the future? The obvious answer: because the past happened and the future hasn't. But in physics, that doesn't work. The fundamental laws are symmetric in time. A particle doesn't know if it's moving into the past or the future. Nothing in the equation says, this is the past, that's the future. So where does this glaringly obvious asymmetry in your experience come from? From entropy. Memory needs physical structure. Remembering means your brain changed, synapses strengthened, molecules rearranged. That took energy and increased universal entropy. Memories are physical marks created only by entropy-increasing processes. You can't remember the future, not because it hasn't happened, but because creating a memory requires an irreversible process. And irreversible processes only exist in the direction of increasing entropy. The arrow of time, the distinction between past and future, does not exist in the fundamental laws. It emerges exclusively from the increase in entropy. And now we get to the central point of this video. Now, add this extra bizarre fact. Combine what we just understood, that the arrow of time is thermodynamic, not fundamental, with what relativity says about the structure of time. The result changes what it means to exist. In relativity, there's the block universe. No privileged present racing through the cosmos. All moments coexist in space-time. Past, present, future are equally real. What you experience as now is just your position in space-time. Other observers moving differently experience a different present, and both are right. All of space-time exists at once. If that's true, and relativity says it is, then the end of the universe already exists. Heat death, 100 years from now, exists in space-time right now. Not coming, existing, just unreachable from where you are. The end of time is already here. Sean Carroll puts it this way: one initial fact explains all our temporal structure. The past hypothesis. The universe started with extraordinarily low entropy. This unique condition is the only thing that transforms reversible physics into time with a direction. Without it, no past, future, memory, causality, or conscious experience would exist. Everything you experience as time, the feeling of flow, that the past is fixed, the future is open, is the shadow entropy casts. The arrow of time isn't fundamental. It's entropy's shadow. Imagine what this implies for the experience of being you. The feeling of being alive in the present, of having a past you remember, and an open future ahead of you. The feeling that time flows. All of this is thermodynamics. It's the subjective expression of a statistical asymmetry that began with an unlikely initial condition 13,800,000,000 years ago. Your experience of time is not a fundamental property of the universe. It is an epiphenomenon of entropy. The universe has a thermodynamic destiny, fixed from the start, written in the second law. What's this destiny? Heat death, maximum entropy, perfect equilibrium where no work is possible because there's no temperature or pressure gradient to use. Everything's the same temperature. No energy flows, no events, no structure, no information. The path there is long, incomprehensibly long. 10 to 14 years from now, 100 trillion years, about 10,000 times the current age of the universe. The last of the low-mass stars will finally exhaust its fuel and fade out. Star formation will have already ceased long before that, as free hydrogen becomes scarce. The universe will progressively darken, star by star, over billions of years, until no new light is ever ignited. But matter's still here. 1034 years from now, a 1 followed by 34 zeros, protons themselves decay. Every atomic nucleus disintegrates. Matter as we know it dissolves. Planets, asteroids, remnants, everything unravels into positrons, electrons, photons. Solid matter ceases to exist. Real experiments in Japan and Canada, using building-sized detectors, monitor protons right now, looking for this decay. They're proof this physics stretches across unimaginable timescales. But black holes remain. Stephen Hawking showed black holes emit radiation slowly. Hawking radiation. Over even longer timescales, they evaporate. A stellar black hole takes about $10.67 years. A supermassive one like our galaxy's core could take 10,100 years. A Google years. After that, cold photons, electrons, and positrons scattered across infinitely expanded space in perfect thermal equilibrium. Nearly uniform temperature. Fractions of a Kelvin above absolute zero. No structure. No gradient, no temperature difference for any useful process, no light, no planets, no ordinary matter, just sparse particles and dying photons in cold, silent darkness forever. No clock ticks. There's no way to measure time because nothing happens. Remember the entropy information equivalence? At maximum entropy, there's no information to process. No information processing means no events. No events means no time. Nothing defines before and after. In physics terms, time stops. So the second law explains everything. The arrow of time, aging, memory, the end. But the more you understand it, the more one question becomes impossible to ignore. But here's where physics breaks common sense. The second law says entropy increases. It explains time's direction, heat death, why eggs don't reassemble. But there's one detail it can't explain: why entropy started so low. The Big Bang didn't have to start with low entropy. By Boltzmann's logic, it should have started near equilibrium. High entropy is the most probable state. Low entropy is improbable. Yet the Big Bang started in extraordinarily low entropy. Roger Penrose, British mathematician, 2020 Nobel laureate in physics, did the math. Given current universe entropy, what's the probability the Big Bang started randomly in this specific low entropy state? The answer? 1 in 10, 123. That's not a big number. It's a number with zero conceptual meaning. Visualize it. The universe has roughly 10 80 atoms. A 10 followed by 80 zeros. Penrose's denominator has 10 to the power of 123 in the exponent. The zeros in that denominator outnumber all atoms in the entire universe. The improbability is incomprehensible at any human scale. This is the initial state of our universe. There are proposals to explain why this happened. Penrose proposed conformal cyclic cosmology. Our Big Bang is a bounce from a previous universe that reached heat death. In perfect equilibrium, with no timescales, no structure, Penrose's equations say the end of one universe's geometry matches a new one's beginning. Entropy resets in this conformal transition. There is the anthropic argument. Only in universes with low initial entropy can there be observers to ask the question. In universes that start with high entropy, no structure forms, no stars, planets, life, or consciousness emerge. We are here because we can only exist in a universe that allows our existence. And then there's the Boltzmann brain, possibly the most bizarre concept in cosmological physics. But here's a question that breaks the purely statistical argument. If random fluctuations create anything, what's most likely? If the universe is infinite in time, random quantum fluctuations will eventually create every possible particle configuration. This includes, by pure accident, a fully formed brain with false memories of a lifetime. An observer floating in the vacuum, thinking they're watching a video, with fake memories of childhood, family, experiences that never happened. Creating this random brain is statistically more likely than creating an entire universe with low enough entropy to produce, over billions of years, a real observer. So if you explain low initial entropy purely through statistics, you predict you're most likely a Boltzmann brain, a statistical hallucination, not a real observer in a real universe. This is a serious problem, a problem that remains unsolved. But there's a clue coming from a completely unexpected place that changed what we know about where entropy can be stored in the universe. In 1972, young physicist Jacob Bekenstein proposed the unthinkable. Black holes have entropy. The problem: throw a book with high entropy, lots of text, lots of information, into a black hole. It disappears. From outside, all that information vanishes. The accessible universe's entropy appears to decrease. But that violates the second law. Bekenstein argued black holes must store entropy internally to compensate. Stephen Hawking, initially skeptical, did the full calculation in 1974. He found something nobody expected. A black hole's entropy isn't proportional to volume. It's proportional to surface area, the event horizon size, the boundary where nothing escapes. The Bekenstein-Hawking formula, S equals k times a divided by 4 times the Planck length squared. Area, not volume. This is profoundly weird. Every other object, stars, gas clouds, planets, scales entropy with volume, with internal particles. Black holes store all information on the surface. The implication is one of the most radical ideas in modern physics, the holographic principle. If volume information is completely encoded on its 2D surface, maybe our entire 3D reality is a projection from that surface. The whole universe might be a hologram, 3D reality from 2D information on a cosmic surface. This brings Hawking's information paradox. Black holes evaporate via Hawking radiation. That radiation's pure thermal noise. When the black hole dies, what happens to all the information from everything that fell in? Destroying information violates quantum mechanics. Best current answer: information isn't destroyed. It's encoded subtly in the quantum correlations of Hawking radiation. The holographic principle ensures nothing is lost. Cosmic accounting balances, but we're still working out the exact mechanism. We're at physics frontier. Now let's bring all of this back to you. In 1944, Erwin Schrödinger, yes, the cat guy, published a short book. What is life? He made an observation that changed biology. Living organisms are negentropy machines. Negentropy is the opposite of entropy. Order, structure, organized information. Schrödinger noted life imports low entropy from the environment, sunlight, food, and exports high entropy as heat and waste. Locally, inside a cell or organism, entropy can decrease. The second law doesn't forbid this. It only forbids a closed system's total entropy from decreasing. Life doesn't violate the second law. It surfs the gradient. It uses the entropy difference between hot sun and cold space to build temporary, local structure. Aging is thermodynamics. Cellular damage, DNA mutations, misfolded proteins, degraded lipids, expresses the second law locally. There's no perfect eternal repair system because repair costs energy. The body fights entropy, but entropy wins over decades. Memory, the core way you experience time, is thermodynamic too. Every memory is a physical brain change. Synapses strengthen. Proteins synthesize. Molecular structures reorganize to encode experience. These are irreversible processes that increased universal entropy. You can't undo a memory any more than unbreak an egg. The irreversibility you feel as memory is the same irreversibility that breaks eggs. Every thought you've had, every connection, every moment registered, every idea processed, increased universal entropy. Your existence, your thinking, you being here, microscopically pushes the cosmos toward equilibrium. You're a whirlpool of order in a river flowing toward equilibrium. A local, temporary structure using the sun's entropy difference to maintain organization, exactly as Schrödinger said, extraordinary and completely thermodynamic. It's time to tie it all together. Here's the cascade. The Big Bang started in extraordinarily low entropy. 1 in 10 billion and 10 to 123, physics' deepest mystery. The second law said entropy only increases. This increase is, precisely, the arrow of time, the only past-future distinction in nature. You have memories because you make irreversible marks, only possible in entropy's direction. The arrow points toward maximum equilibrium, heat-death, where no process, memory, or event exists. Time's end was fixed at the Big Bang. In relativity's block universe, where all moments coexist in space-time, heat-death already exists. Not coming, existing. Just unreachable from where you are. The end of time is already here. But what keeps the brightest physics minds awake is the other end. Why did the universe start in such an improbable state? Why was entropy so low at the Big Bang? The second law explains everything after, not the beginning. Penrose, Hawking, Carroll, and dozens of brilliant minds keep working, proposing cyclic cosmologies, anthropic multiverses, new thermodynamic principles, physics beyond the standard model. Every proposal solves one problem, creates another. The question remains. This doesn't mean physics failed. It means the universe is stranger, deeper, more extraordinary than we can frame. The more precise the question, the more impossible the answer seems. And that's not ignorance. That's getting close to something real. Here's the terrifying consequence the Boltzmann brain leaves behind, even discarded as cosmology. You can't prove your memories match a real past based on your experience alone. The only reason to believe they do. The universe began in a nearly impossible entropy state. Your entire past, every memory, experience, every moment that made you, rests on this single fact. 1 in 10 Brits, Satu to 10. 1 read to 123. The second law of thermodynamics is physics' strangest law. It's the only law that knows past from future. It's why you have memories, why stars shine, why you exist. And it wrote the end of the story before the story began. The end of time is already here. You're watching this in an instant that coexists in space-time with 10,100 years of silence. Not metaphor. Physics. If this grabbed you, subscribe. We explore where physics stops being abstract and tells you what's real. Comment which part blew your mind. Entropy's arrow, Penrose's number, the Boltzmann brain, or that the end already exists in space-time right now.